Hi friends, welcome back. In the previous session, we have seen Fourier transform. In that Fourier transform, we have seen some properties of the Fourier transform. So let's continue with the Fourier transform only here. And we are going to see some more properties here. Okay. So let's see the next property, frequency differentiation property. Frequency differentiation property. What is frequency differentiation property? As we know, in the time differentiation property, this is what we know. Suppose if x of t having Fourier transform x of omega, then dx of t by dt having Fourier transform j omega multiplied with x of omega. So here, if I do the differentiation in time domain, we have to multiply with j omega in the frequency domain. That's what we have done in the time differentiation property. Let's come to the frequency differentiation property. In this frequency differentiation property, suppose if x of t having Fourier transform x of omega, then if I consider dx of omega by d omega, then what is the inverse Fourier transform for this? What is the inverse Fourier transform for this is? So in that time differentiation property, we have multiplied with j omega. In the frequency differentiation property, we have to multiply with minus jt. So j omega jt, but with a negative sign. So it is minus jt x of t. But nobody remembers this kind of formula. But the simple thing is t x of t. For this, what is the Fourier transform if I ask? So if I bring this minus j to this side, this will become plus j. So j dx of omega by d omega. So this is what the property you have to remember. Take it. Let's see one example. Fourier transform of t e power minus at u of t. For this function, what is the Fourier transform? How we can calculate that? So I can use the frequency differentiation property. So let's see what we know first. We know e power minus at u of t. We know this one. For this one, the Fourier transform is 1 by a plus j omega. 1 by a plus j omega. Now we have to calculate what is the Fourier transform for t e power minus at u of t. That means we have to take j d by d omega 1 by a plus j omega. 1 by a plus j omega. So for this one we have to calculate. So let's see, this is nothing but j. So minus a plus j omega whole power minus 2 into j. So this is what the differentiation. So if I multiply with j and j, that is going to become minus 1 and minus. So finally we are going to get 1 by a plus j omega whole square. 1 by a plus j omega whole square. So you have to remember this as a standard formula. T e power minus at u of t having Fourier transform 1 by a plus j omega whole square. 1 by a plus j omega whole square. You have to remember this. Clear? Take it. T power n e power minus at u of t. For this, what is the Fourier transform is? N factor by a plus j omega whole power n plus 1. Whole power n plus 1. So this is also one standard formula you can remember. Let's take one example. Find Fourier transform for x of t. This is what x of t. For this signal, I want to calculate Fourier transform x of omega. Okay. I told you, whenever a signal is existing only for positive values of time, that means we have to multiply with u of t. Whenever a signal is existing only for negative values of time, then we have to multiply with u of minus t. But what if the signal is existing for a finite duration? Then we have to multiply with a rectangular pulse. A rectangular pulse. So here also, if I say, let's call a signal let's say t, a signal t itself. So t means it is a straight line passing through origin. It is a straight line passing through origin. So this is the signal what we got. So here the slope is equal to 1. Slope is equal to 1. Now, if this signal is multiplied with a gate pulse, which is existing between -1 and +1, let's call it is g of t. Now, if you observe carefully, if I multiply this signal g of t with t, can I get x of t or not? Yes, definitely I can get x of t. So I told you, whenever this is nothing but straight line passing through origin, but it is existing only between -1 and +1. So this is the thing we have to understand. G of t is multiplied with t, then we are going to get x of t. First, then how we can calculate the x of omega here. So for that, let's see, what is g of omega? G of omega. We know for a rectangular pulse, what is g of omega? Area sampling width by 2 omega. What is area? 2 into 1, 2. Sampling width by 2, 1 omega. So this is what we got, g of omega. Then what is x of t? So let's say g of t having Fourier transform g of omega. Then Tg of t. Tg of t. This is nothing but the x of t, right? So if I multiply t into g of t, that is going to be x of t. For this, what is the Fourier transform? We know from the property of differentiation in the frequency domain, we can say for Tg of t, we are having j d g of omega by d omega. So I can say j d by d omega. What is j of omega? 2 sampling omega. 2 sampling omega. So if I take 2j d by d omega sine omega by omega. So this is what the Fourier transform. If you want, you can simplify still it by using the u by v formula also. But still, I am just stopping here because you can understand how to do this one, u by v formula. Okay. So take it. This is the Fourier transform x of omega. Next example, find Fourier transform for of x of t is equal to e power minus pi t square. E power minus pi t square. It is not a simply exponential, it is e power minus pi t square. Okay. So what is the signal e power minus pi t square? You might see this function in the mathematics also, or in the communication systems also. You can see this function x of t is equal to e power minus pi t square. What is this function? If I say this is nothing but Gaussian function. This is called as Gaussian function. So here x of t is nothing but Gaussian function. It is called as Gaussian function. If I draw this function, how it look like with respect to t? At 0, its value is equal to 1. If t value increases, its value keep on decreases, its value keep on decreases. So finally, you are going to get a bell-shaped curve. A bell-shaped curve. A bell-shaped curve. So this is called as Gaussian function. So for this Gaussian function, I have to calculate what is a Fourier transform. So it is not in the standard form, so we have to use so many rules here. So let's see one by one. So they have given x of t is equal to e power minus pi t square. What if I say dx of t by dt, if I do the differentiation? This is minus 2 pi t into e power minus pi t square. So that's what the differentiation for this. And e power minus pi t square is again equal to x of t. So I can write that implies dx of t by dt is equal to minus 2 pi t x of t. 2 pi t x of t. Now take Fourier transform on both sides. Take Fourier transform on both sides. If I take Fourier transform on both sides, what I am going to get? For dx of t by dt, I am going to get j omega x of omega is equal to minus 2 pi. X of t is having x of omega. What is t x of t? That is nothing but j d x of omega by d omega. So that's what it is. So j get cancelled. Finally, what we are getting is omega x of omega is equal to minus 2 pi dx of omega by d omega. If I take cross multiplication, omega terms one side and x of omega terms one side, then it is going to be minus 1 by 2 pi omega d omega is equal to 1 by x of omega d x of omega. That is what we are going to get. Or if I write this one this side, this one this side, then this is going to be 1 by x of omega dx of omega is equal to minus 1 by 2 pi omega d omega. So this is what we got. So x of omega terms one side and omega terms one side. So now if I integrate on both sides, integrate on both sides. Integrate on both sides. You tell me. 1 by x dx. What is the integration for this? ln x. So ln x of omega, natural logarithm. And for this one, this is nothing but minus 1 by 2 pi omega square by 2. Omega square by 2. That is the integration for it. So in short, what is x of omega? Exponential e power minus omega square by 4 pi. Omega square by 4 pi. So this is what x of omega you are going to get. X of omega. But what if I want x of f? X of f in f domain. This is going to be e power minus omega can be replaced with 2 pi f whole square by 4 pi. So this is nothing but 4 pi square f square. So 4 get cancelled, 1 pi get cancelled. Finally, what we are left with is e power minus pi f square. So this is x of f. X of f. So x of f is equal to e power minus pi f square. E power minus pi f square. So this is what we got, x of f. So this is a very important thing you have to remember. Why? Because if you observe x of f and x of t, both are same. Only in place of t we have replaced with f. So can I simply say x of t is a Gaussian function, whereas x of f or x of omega are also Gaussian functions. So if I draw this function with respect to f, so I can again get a bell-shaped curve. Okay. So this is what x of f. So which is also Gaussian function. Gaussian function. So here one very important thing is the Fourier transform of a Gaussian function is again will become a Gaussian function. So here it is easy to remember x of f because x of f is equal to e power minus f square. So simply we have replaced t with f. Sir, what if I want x of omega? So simply replace f with omega by 2 pi. If I replace omega by 2 pi, then we are going to get this function. So I hope you understood what I am trying to say. So it is easy to remember x of f instead of x of omega. So whichever you feel it is comfortable, you can remember. But I am suggesting remember x of f. So because in this one simply e power minus pi t square having x of f is equal to e power minus pi f square. So if you could remember this one, from this you can get x of omega also. I hope you understood. Okay, take it. Find inverse Fourier transform of example. Find inverse Fourier transform of j d by d omega e power j 2 omega by 1 plus j omega by 3. For this, we have to calculate inverse Fourier transform. That means they have given in frequency domain, we have to calculate t domain. So I told you I always represent time domain in the left side and frequency domain in the right side. So I will go in the same way. Okay. So let's see, I will take the basic thing what we know. 1 by 1 plus j omega by 3. We don't know this one, but we know one thing. Suppose 3 by 3 plus j omega. 3 by 3 plus j omega. This is what we know. 3 by 3 plus j omega. So for this, what is the inverse Fourier transform? The inverse Fourier transform is 3 e power minus 3t u of t. Okay. Now, if it is multiplied with e power j2 omega by 1 plus j omega by 3. We know up to this one, if it is multiplied with e power j2 omega, then we have to take a time shifting property here. So what is the time shifting? It is t has to be replaced with t minus 2. Then 3 e power minus 3 t minus 2 u of t minus 2. That's what it is. Next, if it is j d by d omega e power j2 omega by 1 plus j omega by 3. Then if it is j d by d omega, here we have to multiply with t e power minus 3 t minus 2 u of t minus 2. So that's it. So this is the inverse Fourier transform. Okay, take it. And I'm very sorry, this is not t minus 2, this is t plus 2. T plus 2, because it is a positive, so we have to shift, we have to advance the signal. Okay, take it. Property. Duality property. Suppose a signal small x of t, time domain signal, having Fourier transform capital X of omega. So here, if you observe carefully, suppose if I take any function x of t, I am going to get x of omega. So it is a function of t, it is a function of omega. What if I take this function in time domain? So capital X function only, but I will take the variable is t. I will take the variable is t. So wherever omega is there, if I replace with t, then it is going to be time domain signal. If it is a time domain signal x of t, duality property is saying that for this, the Fourier transform is nothing but 2 pi small x of minus omega. That means in this signal, we have to replace t with minus omega and we have to multiply with 2 pi. What is minus omega? That means we have to fold the signal. So we have to fold the signal and multiply with 2 pi. That's what the meaning of it. So this is one duality property in terms of x of omega. What if I take x of f? For x of t, we are having x of f. Then in the duality property, capital X of t, that is, if f is replaced with t, then we don't have this 2 pi factor, simply small x of minus f, small x of minus f. So this is the duality property. Just to make you understand, let's see. Suppose if somebody is asking Fourier transform of 1 by a plus j t, if I say 1 by a plus jt. So by directly saying that, so we don't know the function actually what is 1 by a plus jt. But if I replace t with omega, that function we know. What do you mean by that? Suppose if I take 1 by a plus j omega. To get this function, what is the time domain? That is nothing but e power minus at u of t. E power minus at u of t. So here, if I apply the duality property, in the duality property, if I replace omega with t, then it is going to be 1 by a plus jt. For this function, what is the Fourier transform? I told you, we have to multiply the signal with 2 pi and t has to be replaced with a minus omega. Then we are having Fourier transform 2 pi e power minus a t plus we have to replace with minus omega. This is going to be a omega u of minus omega. So this is the Fourier transform for 1 by a plus jt. So I hope you understood how to apply the duality property. Suppose if I ask the same thing, let's say 2a by a square plus t square. For this function, I want the Fourier transform. What is the Fourier transform for this function? Okay. Now, by directly saying this function, we don't know. But what if I replace with t with omega? Then we are having 2a by a square plus omega square. So to get this function, what is the time domain expression? That is nothing but e power minus a mod t. E power minus a mod t. Now, if I apply the duality property here, so this is nothing but 2a by a square plus t square. In place of omega, if I replace with t, then what we are going to get here? What is the Fourier transform for this? 2 pi. Wherever t is there we have to replace with minus omega. So if t is replaced with minus omega, will it make any difference? No, because mod minus omega is nothing but mod omega only. So e power minus a mod omega. So this is what the Fourier transform for this function, 2a by a square plus t square. Clear? Take it. If I ask, what is the Fourier transform for sampling a t? Sampling a t. We don't know what is the Fourier transform for sampling a t. But if I apply the duality property, suppose if I assume sampling a omega, to get this function sampling a omega, what is the function in the time domain? So I know to get a sampling function, it must be a rectangular pulse, symmetrically located rectangular pulse in the time domain. So let's call it as x of t. So what is x of t here? It is a rectangular pulse. I can understand up to this. Now, what does this a indicate? That is nothing but width by 2. So what is the width here? 2a. Then it is going to be minus a, 0, a. I hope you understood what I am trying to say. A indicates width by 2. So if it is width by 2, what is the total width? 2a. So if it is total width 2a, if it is symmetrically located, then it has to be minus a and plus a. Next, here the coefficient is 1. What is this coefficient? 1 indicates area under the rectangular pulse. So the width is 2a. What should be the height so that its area will become 1? I hope you understood what I am trying to ask. The width is 2a. What should be the height of this rectangular pulse so that its area will become 1? So that is nothing but 1 by 2a. 1 by 2a. I hope you understood. Now, for this one, if I apply duality property, sampling a t, then what is the Fourier transform for this? So for this function, we have to multiply with 2 pi and I have to replace t with minus omega. What do you mean by t is replaced with minus omega? So this function has to be folded. Because it is an even function, even though if I fold it, it won't make any difference. I am going to get the same function. So I am going to get in omega domain again a rectangular pulse only. So let's say this is a Fourier transform. How it is going to be? If I fold it, it won't make any difference. It exists between minus a and plus a only. But we have to multiply with 2 pi by 2a. So which is nothing but pi by a. Pi by a. So this is what x of omega we got. For this function, this is the Fourier transform. Okay. Now, if I ask a special function, let's say Fourier transform of sin at by pi t. Sin at by pi t. What is the Fourier transform for this function? So this is a very important function, I can say. Sin at by pi t. Why, you can understand in a moment. Sin at by pi t. So listen here. Can I write sin at by pi t as a by pi sampling at? I told you the coefficient is a here, the coefficient is pi, so a by pi sampling at. For sampling at, we got this is a rectangular pulse with a pi by a is the amplitude. Sampling at, we are going to get the same, but if it is multiplied with a by pi, then if I multiply with a by pi, a pi get cancelled, finally the amplitude is going to be 1. So for this, the Fourier transform is again a rectangular pulse minus a, 0, a and 1. Okay. So this is what the Fourier transform for sin at by pi t. If I ask, suppose a system, let's say system h of t is equal to sin at by pi t, having h of omega. What is h of omega here? It is nothing but a rectangular pulse minus a plus a 0 1. So this is what h of omega. What is this system indicate? What is this system indicate? So if I ask, then this system indicates low pass filter. Why? See, if you observe carefully, it is allowing the frequencies only between 0 to a. So I can say, and it is having a pass band gain is equal to 1. So it's an ideal low pass filter with cutoff frequency a radians per second and pass band gain is equal to 1. So that's a very important thing. So even sampling at is also a low pass filter with a cutoff frequency a radians per second, but the pass band gain is not equal to 1. What is the pass band gain here? It is nothing but pi by a. It is nothing but pi by a. So that is the difference between sin at by pi t and sampling at. Both are low pass filters only, but this is called as ideal low pass filter. Why it is called as ideal low pass filter? So it is having sharp cutoff characteristics and pass band gain is equal to 1. So I can simply say this system indicate ideal low pass filter. So whenever you see h of t which is equal to sin at by pi t, sin at by pi t. So you just have to remember it is nothing but ideal low pass filter with a cutoff frequency a radians per second is ideal low pass filter. with cutoff frequency omega c is equal to a radians per second. A radians per second. So whenever you see sin at by pi t, you just have to remember it is a low pass filter with a cutoff frequency, and pass band gain is equal to 1. And pass band gain is equal to 1. Clear? Take it.